The process of resolution of vectors means, and we oftentimes will say to resolve a vector, means to break it down into components. In other words, into the form we just saw, from something that might look like this: 3 meters per second at 15 degrees into some I hat plus j hat form. That's the resolution of vectors. Scalar multiplication of vectors is pretty much just an application in the distributive property. (73.5i) plus 170.1j. Essentially what you're saying is you have 21 of these things laid end to end. So what does it look like? Well, it's the same thing as saying you have one of these that is 21 times as big. An automobile is capable of accelerating at 1.45 meters per second squared. At this rate, how long will it take to accelerate from 50 kilometers per hour to 100 kilometers per hour? So we're going to have to do a unit conversion first. I went up here to the top. So 50 kilometers per hour. Well, if you remember from earlier, 1 hour is 3,600 seconds. And I'm going to show you a cheap way, if you remember your prefixes, of handling a conversion with a prefix. K is 1,000. So there's 10 to the third. All I need to do is directly replace the K with 10 times 10 to the third, and I'm good. That gives us meters per hour. Now I can simply multiply by 1 hour over 3,600 seconds. So 50 kilometers per hour is 13.89 meters per second. And all I need to do then is double it so that 100 kilometers per hour is equal to 27.78 meters per second. I had to change pen, sorry. So now, acceleration is equal to VF minus VI over T. I know my acceleration is 1.45. My final speed is 27.78. My initial speed was 13.89. And I'm looking for my time. So that my time is simply going to be (19.16 seconds). Since that's 3 significant digits, but the way each of these is written is only 1 significant digit, that says my time is in fact 20 seconds. There's no decimal point here, there's no line over it, so I'm only showing 1 significant digit. In the process of stopping, car leaves skid marks 87 meters long. The car is known to have a constant acceleration of a negative 6.75 meters per second squared, which is really what we'd commonly call a deceleration. How fast was the car traveling? So in this case, we have a delta x is 1/2 at squared plus vit. 87 meters is equal to 1/2 negative 6.75 t squared plus vit. Now that is our first thought as far as approaching this one. That's not going to help us. We don't know the initial speed. We don't know the time. So in fact, this is one of the situations where the algebraic combination is useful. Vf squared minus Vi squared is equal to 2a delta x. The thing about the algebraic combination is it does not give you a positive or negative in the calculation for speed. This is a speed only, so you would have to get the direction somewhere else. In this case, since I only ask for speed, how fast, we're fine. So it stopped. Process of stopping. So our final speed is in fact 0. So 0 squared minus our initial speed squared is equal to 2, negative 6.75, and it went 87 meters. So I have a negative Vi squared. Now the negative is not under the square, so it does not get squared. It's equal to a negative 1,174.5 meters. Now you want negatives on both sides, otherwise you end up with imaginary or complex answers, and we don't typically expect to have that for a distance. Excuse me, that's meters per second. Meters squared per second squared. So that gives me a speed, an initial speed of 34.27 meters per second. 3 significant digits, 2 significant digits, and defined to be 0 means I should have 2 significant digits, so that gives me an initial speed of 34 meters per second. A stone is dropped from a cliff and falls, grammatical error, 2.35 seconds. How high is the cliff? Well, same thing. We have a time here, so we have a delta y is equal to 1/2 at squared plus vit. Now, there's nothing in this to lead you to believe that this problem does not occur on the Earth. So we can, in that situation, assume we're dealing with the Earth and we have an acceleration due to gravity of a negative 9.81 meters per second squared. Delta y is 1/2 negative 9.81, 2.35 squared. It's dropped, so your initial speed is 0. Now, oftentimes I don't write this term, but I am writing it this time, just for completeness. .087 meters. 3 significant digits, 3 significant digits, defined as 0, so we need 3 significant digits, so 27.1 meters. These have a negative, sorry I forgot to write that down, which makes sense because the negative indicates it's going down. If you've ever dropped anything, you know that things fall down. A child throws a ball straight upward and catches it 2.88 seconds later. How fast did she throw the ball? Well, think about what the ball did. The ball went up, the ball went down. It should take just as long to go up as to come down. So it's taking 1.44 seconds each way. At the top, what would the speed be? Well, so if we think about just the going up piece, the final speed should be 0. Now, why can I say that? Well, simply put, because if not, it's still going to go up. So I can say that the acceleration is delta V over t. No reason to assume she's throwing a ball anywhere but on Earth. Now the final speed as it goes up is 0. That leaves me with a negative VI over my time, which was 1.44 seconds just to go up. Multiplying, that gives me 14.126, and that's a negative, is equal to a negative VI. So 14.126 is VI. Three significant digits, I should have 3, so 14.1 meters per second is VI. And again, typically I do not carry my units in the calculation. I find that just clutters it up. Occasionally, if I need to double check units, I'll do a unit analysis off to the side, which is where I carry my units all the way through the calculation, but no numbers.